Right, welcome everyone to my talk, which is not about chatbots, but we're going to talk about search instead. And why is search important? We're going to find out. You can connect with me on LinkedIn or Twitter or whatever we call it nowadays. I'm on every social network, so please feel free to connect with me. I'm a developer advocate at MongoDB. I have my colleague here, Surab from MongoDB as well, so if you want to chat with us about databases or about AI, we'll be here all day. Enough about me. So these are the slides for the application, and if you want to follow along or just keep them for later, you can scan that. It will be over there at the end as well, but yeah, don't feel pressure to scan it out. Couple more seconds? No? Okay. All right, so why is search important? Research shows that 87% of all shoppers in e-commerce websites first go to the search bar. They want to find what they're looking for, and this is the first place that they go. They don't care about all the UX optimizations that you've done. They don't care that much about speed performance. They care about finding what they're looking for. And the same research shows that if the shoppers don't find the result that they're looking for within the first search page, they just leave. 68% of them directly go to your competitor and buy what they need over there. So in short, this is why search is important and why I want to talk about it today. I think it's a bit more important than customer service chatbots or by all the cool AI innovations we have. We can really start talking about the basics and start from there and optimize our sales performance there. There are many ways to search for data, and as developers, we're probably familiar with them. We can search by using regexes through our full-text search in the data in our database. But that is a naive approach. It doesn't scale well. We can also use something like Elasticsearch or Solr, which are all based on full-text search on Lucene. So when we're doing that, we're actually using keyword-based search. Or we can use something called semantic search, which is what we're going to be talking about today. But before jumping on to semantic search, let's talk about the keyword-based search. And let's see why our use case might be good for semantic search. See this example. So we are using keyword-based search over here, and we are searching for interesting places to visit in Manhattan, New York City. And we get the following results. So we get 20 best attractions in Manhattan, best places to visit, top Manhattan restaurants, Manhattan travel guides. That all seems good, right? These are good results. But we might also get the result, visit Manhattan Beach in California. And as you can see, this is not really relevant to our search query because we're looking for a different Manhattan. Why does that happen? Well, because keyword search doesn't understand the semantic meaning of our query. It doesn't understand the connection of the query that we typed, the meaning of the sentence. It is working based on the individual words. And it might take into account some synonyms, and it might take into account typos or stuff like that, but it doesn't have the capability of actually understanding the query that the user typed in. Another example where keyword search is not going to do the job is if we want to search for unstructured data. How do we search for a video? How do we search for an image? How do we search social media posts? These are all examples of unstructured data, and they are not trivial to implement with keyword-based search. A way to make that work with keyword search is to tag these images. So if we have the image on the left, and to make it understandable, we can add different tags. So we can say this is an image, this is a landmark, and it has the following tags: New York, Manhattan, Brooklyn. That way, when we search for Manhattan, it's going to show up. But again, we're using text search here, and we need to do that manual tagging. Similarly, for videos, we can add tags and we can add the types of landmark that we have, and similarly for audio. But again, we need to actually use text to define this data. So there must be a better way. And that way is to understand the meaning of the query that the developer typed in the search box. How can we do that? We can do that with a technology called vector search. Vector search solves the challenge of providing us relevant results even when we don't know what we're looking for. And it uses under the hood machine learning models to find results that are similar. So it still doesn't understand exactly what we mean, but it can boil down the essence of the query to a mathematical model that can be compared to other results. It sounds a bit tricky, but we'll see that it's actually really easy and it boils down to simple distance calculations. Vector search has a lot more use cases in the industry nowadays. We're going to focus on semantic search and image search, or more specifically for searching for unstructured data. And the easiest way to understand that is by seeing a demo of semantic search. So over here we have this really simple book catalog. So we have a search bar and we have a bunch of books that we can look for. Let's see what happens when we query for a book about Greek philosophy. We get some results. Unsurprisingly, the first result is a book called Early Greek Philosophy. So no surprise there, obviously it's about philosophy and we got it as the most relevant result. We also get a relevance score. We can see that this is the highest score, so this is the result that we get first. Nothing surprising there. But let's focus on the second book that we got in these results, and this is where it gets really interesting. So you can see here that we got a book about Spinoza. Spinoza is a Dutch philosopher from the 15th century, and nowhere in this book title or description or authors we have the words philosophy or Greek. However, we are using semantic search. So this book has generated a mathematical vector that is close to the words philosophy, because the model that generated this vector has the context. It has the context that Spinoza is a philosopher. Right, let's see how we can actually make that happen. We'll start from the beginning. What is this vector thing? Let's say that we want to locate a product in a supermarket. The location can be defined by a vector, and the first member of the vector is the aisle, and the second member of the vector is the bin, where this product lives. So this is how we describe the location of an object. And this is an example of a two-dimensional vector, because we have two parameters in there. Another example of a vector are GPS coordinates. We can have 2D or 3D vectors here. And again, we define location. Objects in gaming can be also defined using vectors, and this is how we can calculate the distance between different objects. We can say if they collide or not, and if we can basically put them on the screen. And the more dimensions, the more numbers we add to that vector, the larger the space gets. And we can easily imagine a one-dimensional or two-dimensional or even a three-dimensional vector, but the more dimensions we add, it gets harder to kind of imagine, to boil down to. But in the end, the mathematics are the same. So if we're talking about a 3D vector or a vector with 2000 dimensions, we are using the same mathematics to calculate the distance between objects. Vectors in machine learning, or the vectors that we are gonna learn about today, are lists of numbers that represent different data points. So here we have a lot more dimensions. And each of the points in the vectors represents a feature. So you can imagine it as, let's say that the second number here describes the color. And from -1 to 1, with the fractional number, we can describe how red that object is. And of course, this is a very naive explanation, but because the data properties can be much more abstract than a simple color. And the vectors in machine learning can be a lot higher. The vectors that MongoDB Atlas supports are up to 2048 dimensions. But again, the mathematics for calculating how close these objects are exactly the same as with two-dimensional vectors. So what are these vectors? So vectors are actually the mathematical representations of some data. We can have the text "the quick brown fox," throw that to a machine learning model, and we're gonna get back some vector. Now, what we're gonna work with is this mathematical representation of the text. And objects that have a close semantic meaning should generate similar vectors. So if we were to take that multidimensional array and plot it on a 2D space, we would see that man and woman are kind of in the same cluster, and then apple and orange are also in the same cluster. They're closer to each other. And we can have multiple clusters. Imagine that for every piece of data in your database or every image in your image repository, you have a vector representation. And we can use different algorithms to identify similar vectors. And the whole vector search thing is all based on this concept of semantic similarity. So we're looking for some object, we type in the query, we convert that to a vector, and we try to find the closest vectors in this space around it. So you can see here that we have a bunch of landmarks, and we have the New York City neighborhoods in one cluster, and then we have another landmarks that are in a different cluster. Why? Because they are similar. And when we look for landmarks in New York City, we're gonna end up somewhere in the correct cluster. All right, sounds like magic, sounds like something we can do, but how do we get these vectors? Like, we can't just type them by hand, right? We have 2000 dimensions, something should generate these vectors. And this is usually done by an encoder or an encoding model. The way it works is we send some data to the encoder. It does its magic. It is trained on a large amount of data. It could be trained through an LLM. And then the encoder outputs a vector. So it's kind of like a black box. We send some data, we get back a bunch of numbers. We don't know how it works, but we trust the provider that it was trained on the right data and it will generate a good enough vector. And we can do that with a bunch of data types, so it's not just for text. We can have a text model that outputs a vector for text. We can have an image model that outputs data for the images. We can even have audio or video models. And what is a lot more interesting is that we can have a multi-model embeddings model, which means that using the same model, we can generate vectors of the same dimension in the same space for both images, videos, and texts, which will enable us to do search by image or search by text. We're going to use a multimodal model today by Google Cloud. So after we generate all these vectors, how do we store them? What do we do with them? How do we perform this search? I'm going to boil that quote a bit. Don't want to read it, but if you're interested, you can check out the article. Basically, you don't need any kind of sophisticated solution to store a simple vector. When it gets hard is when you want to store tens of thousands or millions of vectors and effectively work with them, index them, make sure that they fit in memory, and make sure that you can search through them. So we need a more specialized solution when we are working with multiple vectors and we want it to scale. So there's a bunch of databases out there that support vector search and that support storing vectors. There are specialized databases, or there are general purpose databases such as MongoDB that has support for vector search. And the reality is that vector search is getting more important now with the last year's inventions in the AI space, and sooner rather than later, every database will be able to offer some further support for vector search. So if you're already using some database, maybe you shouldn't go in and throw another vector database in your tech stack. Let's see what happens if you do though. So you have your transactional database, you have all your application data over there, and then if you decide to add a vector database alongside, this will be nice, it will work well for your use case, but then you will have to eventually go and try to synchronize them. So you have your database, you have your vector database, you have new data, you have to implement some ETL pipeline, move your transactional data, create vectors for it, store that in the vector database, make sure it's up to date, and at some point this gets a bit cumbersome. So a much better way would be to store everything in one place. And this is what MongoDB Atlas offers. So you can have your production data and you can have your vector data in the same database, in the same collections, and you can still have the same kind of simplicity. You don't need to try and integrate two different technologies. So let's see how the application that I showed you works. And this is a universal architecture that you can use if you want to implement vector search. So there are 3 steps. First, you need to generate these vector embeddings. Then you need to build some search index that you're going to use for performing vector search. And finally, you need a way to query the database. You need a way to search. How do we generate embeddings? So let's say that you already have all of your data in your database. You can have a simple generation script that goes to your database, gets all the data, sends that to a Google Cloud function or any serverless function, and then the function goes to the model, sends your text data or your image data to the model, and gets back the embeddings. Then you store these embeddings inside the same database collection alongside with your data. So this is the data that you have in your database. You can get all the meaningful text information from it or the image. You see that there is also a thumbnail. Combine that, send it to the model to generate the vector. Sending it to a model is nowadays as easy as calling the appropriate SDK. So Google Cloud has a Python and a JavaScript SDK that you can use to say just get embeddings and you will get back a vector for your piece of data. So you get these embeddings and you put them back into your database. And the embeddings, as you can see, are just a large array of numbers. Now, the second part is building a search index. And this is a special search engine, so it has to understand that these are vectors and it has to be able to work with vector search. You can do that by creating a new vector search index in MongoDB Atlas in this example. It's very similar for every other vector database out there. So you specify the type, it's a vector index. You specify the number of dimensions, how large is the vector. You specify the field where this vector is inside your documents. And finally, you specify a similarity function. And finally, you can send a search query. So how do we send it? The most important thing is that first we need to get our object that we're searching with. It could be the text query or it could be the image. And we need to create a vector embedding out of it. So we send that back to the same function that generated vectors for all of our data in the database. We get the embedding for the query, and we perform vector search by using, in this case, collection.aggregate, which is the standard way of searching for data in MongoDB. There are a bunch of parameters that you can configure. If you're interested in what any of these means, come and talk to me afterwards. But basically, it's as simple as that, like 10 lines of code and you perform vector search. Let's see how the architecture would look like if we put it in, like if we want to see the bigger picture. So we have our app, we specify the image or we specify the search term. This goes back to the Google Cloud function, which calls our embedding encoder model API. Gets back the vector, and now we can work with this vector. We use the MongoDB driver to perform search. Then the MongoDB driver actually goes to the vector search index, gets all the results that are relevant, the results with the highest score, the results that are closest to our query, and returns them back to our application. This is a blog post that describes exactly the same architecture but using a different technology, and this is just to prove that it's not something that they came up with. It can be used with any sort of vector database, any sort of model, and any application. The slides again, why is this here? Because I have a tiny workshop for you if you want to try it out later at home. There's like a bunch of steps that you can go through and complete the workshop. So scan the slides, and at the very end there's like 5 slides with instructions on how to make that work for you. And if you want to see what you're actually going to be building at home when you go and build it, which I'm confident everyone will do, I'm going to show you the application. All right, so the application is connected to my database. You can see that here in my base, if I can scroll, this is tiny. So my database has a bunch of books. We have title, authors, book ID, and so on. And we also have the vector embedding. So this is how it actually looks like in our database. A bunch of numbers. That's a simple vector. So the application is connected to this database, and it's an Angular application, very similar to the demo that we saw in the beginning, a bunch of books, and we can search through them. So we can search either with text or by providing an image URL. So let's search for, what was it? History, I don't know. Please work. As you can see, we have our app running here. That's the Node.js app and the Angular frontend. And if I come back here, you can see that we got some results. So we got a book called Timeline. It sounds related to history, so I'll take it. We have also London, a novel. So that's like a book about London. Let's try searching for images. So this is the book cover of The Lord of the Rings. And I can provide it over here in this field, wait for our cloud function to get some results. It's still doing its work. You can see that we got some embedding and we got some results. So you can see that we got another book by Tolkien, one more by Tolkien. And you can notice that we actually have books in different languages here. So the cool thing about semantic search is that it actually resolved the problem of having to translate your queries. So that's it. That's the tiny application that you can build yourself if you follow these 5-6 steps over here. There are solutions as well. If you don't want to go through the trouble of coding it yourself, you can just copy the solutions and build it at home. Again, the slides if someone missed them, and thank you. That was everything I have for you today.